Hello everyone. Welcome to this course on pandas versus polars, um, the ultimate battle for high performance in Python. So pandas and polars are two of the most important data science packages in Python ecosystem. Pandas being the oldest and polars introduced recently. So they are used to uh, do data analysis, do lots of data cleaning and data transformations. Uh, so they are used most frequently in data science tasks. So basically, as the amount of data collection is increasing every day, the data sets are becoming bigger and bigger, and the tools that are required to analyze the data need to be very robust and efficient. So pandas is most commonly used for that scenario. However, as the data collection rate increasing and data sets becoming bigger, uh, pandas often has some shortcomings. So polars is introduced recently to overcome those shortcomings, and I will discuss in this course what are the strengths and limitations of pandas uh, versus polars, which one to use in which situations, and I will discuss the data structures of both of these packages in Python. So let's start. All right, something about my background. My name is Muhammad Adil Sultan Khan. I work as a data scientist in Silicon Valley, in San Jose, California, here, and I have over 5 years' experience in my current role. Um, I've completed my master's in information systems in data science analytics from Santa Clara University, California. I also have MBA in data science and finance from San Jose State University, and before that I have cleared CFA level 1 exam, and I also hold computer science undergraduate degree and another master's in information systems and business administration from Institute of Business Administration in Pakistan. So, the agenda of this uh, presentation or course is that in segment one, I will introduce you to pandas versus polars, um, and I will basically discuss. I will introduce you to pandas, how pandas work in data science tasks. So anybody among you who is not familiar with pandas can also understand its functionality. Then I will give introduction on polars, and I will discuss what makes polars faster and more efficient than pandas, and why polars is more efficient for large data sets, how polars handles larger than RAM data, and what is polars query optimization claim. In segment 2, I will discuss the strengths and limitation of pandas and polars, their syntax and their speed comparison, and how can we improve data mining performance using each one of them. And finally, I will discuss when to choose polars, like in which situations polars is a stronger candidate than pandas. And I will give you some examples of multi-threading and parallel computing. Um, I'll show you a demo in Jupyter Notebook using Python, both pandas and polars, their performance benchmarks. So stay tuned, and I will I will show you the functionality of both of these packages. Alright, so what is Pandas? Pandas is Python's powerful and open source data manipulation and data analysis tool. Um, its key functions are data loading, aligning, manipulating, and merging. Pandas has two data structures: series, which is a column, and data frame, which is which has multiple columns or multiple series. Pandas nowadays has use cases in every field: finance, stats, healthcare, engineering, or sensor data. We can use pandas for data cleaning and data analysis each one of those fields. And pandas help in the most complex data transformation tasks, no matter how complex the data set is. We can use pandas to do data transformation and data cleaning and data analysis. Pandas helps in preparing data that is used for building ML and AI models. So we can use this package in all aspects of data science. So pandas data types are that it's if you have a tabular data with heterogeneously typed columns, meaning each column is of different data type, or a SQL table or Excel spreadsheet, or if you have ordered and unordered time series data, we can use pandas to sort the data in whichever way we want. And we can also change the frequency of data if it's a time series data, like from hourly to minute or to seconds or 30 second or 60 second and so on and so forth. Um, and any other form of observational statistical data, if you have, we can use pandas. And also, data need not to be labeled at all to be placed into a pandas data structure. We can use pandas to label the data as well if it's not already labeled for you. So the main tasks of pandas is that it allows easy handling of missing data. If you have lots of null values in your data set, we can use pandas to fill those gaps. Um, we can use pandas to insert columns or delete columns from data frames and other objects. It allows you to have automatic and explicit data alignment. Objects can be explicitly aligned to a set of labels, or the user can simply ignore the labels and let series data frame align the data for you in computations. Um, it's very powerful, and it has flexible group by functionality that we can use to do lots of statistical aggregations on the data. Like we can group by categories, and we can use mean, median, and other measures to aggregate the data with respect to each category in your data. It also allows you to make it easy to convert ragged and differently indexed data in Python and NumPy data structures and convert it into data frame objects. Then also we can do merging and joining data sets. We can do lots of reshaping and pivoting of data sets. We can do hierarchical labeling of access, and we can read data from any source, from databases, from CSV files, and then we can also write data to those different formats. For time series data that we usually get from sensor data or IoT devices, we can generate dates and convert frequencies. We can use rolling window statistics and and lots of other methods for our data analysis. And then we can also use label-based slicing, fancy indexing, and subsetting of large data sets that allows us to analyze data and to to basically slice and dice the data to whatever way we want. This shows you how we select rows and columns in a data frame. You can see the horizontal are the rows, and the vertical we read the columns, and we can read data from any format: HTML, CSV, Parquet, JSON, and then we can also write it to those formats. This shows you a quick overview of one of publicly available data sets, which is a Titanic data set. So in the top right um, um, cell, we are reading a Titanic CSV file, and then we are just reading the top 4 rows of it, top 5 rows. And then on top left, what we are doing is we are aggregating the column age to calculate the mean age of all the passengers. And then in cell 5, we are calculating the median of 2 columns, age and fare. And then in cell 10, we are um, using group by for male and female and aggregating their ages to calculate mean values to determine what were the mean ages of each of the uh, uh, sex traveling in Titanic at that time. And in the bottom right side, we are calculating all the statistical measures for age and fare, min, max, median, and skewness. So this was a quick overview for data mining using Pandas. So this shows you the packages information of Pandas. The most recent package introduced was in on April 10th. The package name was 2.2.2. So basically, Pandas is coming up with different functionalities to compete with Polars. And Polars, as we'll see shortly, was introduced to overcome some of the shortcomings of Pandas. However, Pandas is also trying to catch up with Polars. So with each of its new package, it's introducing new and better ways of analyzing data to overcome its shortcomings. Alright, so what is Polars? Polars is a high performance data frame package for data analysis. It is designed to be faster, efficient, and provide parallel processing. It is suited for larger than memory datasets, like greater than 1 GB at least. And it's a language written in Python and Rust. Rust is another package. I will discuss shortly what is Rust as well, what are the benefits of using Rust for Polars. And that's what makes Polars fast and memory efficient. Polars is designed to utilize all the available CPU cores to allow parallel processing of data. And it also provides smooth transition from Pandas with minimum hassle. So if you are using Pandas, you can easily switch between Polars and Pandas and back and forth as per your requirements. Polars enhances performances and it utilizes machine resources efficiently. And there are 2 modes of operations available in Polars. Lazy evaluation, which basically allow you to delay query execution until you need the output from that part of the code. However, Pandas does eager evaluation, which means it execute all the code right away. So what is the purpose and function of Polars? So the goal of Polars is to provide lightning fast data frame library that utilizes all the available cores on your machine. It optimizes queries to reduce unneeded work and memory allocations. And it allows you to handle datasets that are much larger than your available RAM. It has an API that is consistent and predictable, and it has a strict schema. So you need to know the data types before running the query. However, Polar combines the flexibility and user friendliness of Python with the speed and scalability of Rust as well. So as I mentioned, it's written in Rust, which gives you a C++ performance and allows you to fully control performance critical parts in query engine. Rust ability to be immediately compiled into machine code without the use of an interpreter can make it faster than Python, and that's what gives Polars its efficient performance and faster performance as it's claimed. So Polars enables you to reduce to make redundant copies. Like if you're reading data frame once, it keeps the image of that of data frame. However, in Pandas, you need to read the data, call the data again and again, which makes lots of redundant copies in the backend. So Polars is designed to avoid that. Polars allows you to traverse memory cache efficiently, and it minimizes contention and parallelism. It processes data in chunks, in batches, and it allows you to reuse memory allocations. Alright, so what are Polar's key features? The key features of Polars are its powerful API, the high performance, the optimized queries, and hybrid streaming that allows you to process larger than RAM datasets. Um, for API, Polars has a wide range of data aggregation and transformation operations, including filtering, sorting, and joining. Um, its high performance is achieved by using multi-threading, um, parallelized data processing, which is executed on multiple threads of core processors. So that's one of the biggest advantages of Polars, that it allows you to divide your job into multiple subjobs or subtasks, and then it assigns each one of those subtasks to different parts of your processors or your CPU. So the benefit of that is faster performance and the efficient usage of all your computing resources, which Pandas does not do as as comprehensively as Polars. Optimized queries, it offers you query optimization techniques using optimized data access patterns and minimize data movement. So the data doesn't have to be moved a lot often as in Pandas in Polars. And again, processing larger RAM datasets, uh, that is achieved by using small batches of data um, for each subtask rather than processing all data or all piece of code at once. Alright, so the key features are um, it allows you to use streaming mode, and streaming implies working on data in batches rather than at once. Streaming is achieved in lazy mode in Polars. So as I just mentioned, Polars has two modes, lazy and eager. And the streaming mode, which allows you to um, process much bigger data sets than your RAM size. Um, so streaming uses batches of data for processing and not all data at once. So as I just mentioned, in Polar support both lazy and eager execution. Eager is used by Pandas, and lazy execution defers operations until results are needed, while eager execution executes operations immediately when called. This is a piece of code which shows you that Polars is reading one file iris.csv, and at the same time it's applying group by on a species column and then calculating mean of sepal width for each one of those species, and then just renaming that column into mean sepal width. So the benefit of that is that instead of reading the whole data set like Pandas does, Polars is just reading the data that you need and not all data from iris.csv. And in the end, it's applying streaming equals to true so that data can be processed in batches. Alright, so to determine which parts of your query are streaming, we can use the explain method, and the bottom cell shows you which part of your code or your data is in streaming mode. So we can see the streaming mode is applying aggregate function on sepal width to calculate its mean, and then renaming it um, from by applying group by on column species and from CSV file called iris.csv. And that's the end of streaming mode. So what makes Polars faster and more efficient than Pandas? Obviously it's performance. It's design. Polars is designed for high performance. That's what the main goal of introducing Polars. And how it does that? It leverages Rust multi-threading, SIMD instruction capabilities, and query optimization. So what is SIMD? SIMD stands for Single Instruction Multiple Data, and it allows single CPU instructions to process multiple data points simultaneously. So that's what SIMD is. Uh, Pandas is primarily single-threaded, mm, which may not be as efficient for large data sets mm, or complex operations compared to Polars. However, combining the ability to do streaming as well as lazy execution, Polars has a strong claim to being the better package for data sets above GB size. Memory model, Polars uses Apache Arrow columnar format as its memory model. Apache Arrow is a very popular memory um, processing or memory storage format, and it allows you to store your memory in columns rather than as rows. Um, and that is what optimized for data processing, for faster data processing than Pandas. However, Pandas has a row-based memory format, and that makes Pandas less efficient for operations. Um, Another things that makes Polars faster and more efficient than Pandas is its syntax and API. Polars has a syntax and API that is similar to Pandas, and that makes it easy for users who are familiar with Pandas to transition to Polars. Polars provides a more extensive set of data types compared to Pandas, including very advanced data types like date 64, date time, and interval, as well as support for custom data types, providing greater flexibility to handle diverse data types. And what is the Rust advantage? Since Polars is written in Rust, it utilizes the benefits of concurrency, which allows parallelism, um, and that allows Polars to use all the machine cores, while Pandas uses only single core for data processing operations. Pandas 2.0 is designed to support Apache Arrow for data memory, thus leading to performance improvements. However, Polars continues to be faster than Pandas 2.0 based on its Rust advantage, on parallelism that we saw, on interoperability that you don't need to convert data into other types in memory, uh, while in Pandas you have to, and also query optimization, which is the way they execute code, lazy or eager. And why it is so fast? Because it's written in Rust and it's based on Arrow, as we just saw. Uh, so Apache Arrow memory format, it's being utilized these days by lots of tools like Spark, Parquet, Drill, Impala, and it's a language independent memory format, and the benefits of Apache Arrow is that it allows you to speed up performance, and it avoids converting data to other formats in data pipeline. It standardizes the in-memory data format. It is memory efficient, like two processes can share the same data without needing to make a copy. Arrow contributes to Polars' fast performance for sure. It was created by a guy called Wes McKinney to address big data set issues that we face with Pandas. It's also the backend for Pandas 2.2, a more performant version of Pandas released this year. So as I just mentioned, Pandas is also trying to catch up. So Pandas is also introducing now its own implementation of Apache Arrow to try to make things faster, like Polars. Um, and that's why the newest package of Pandas released in April this year, 2024, it's built on PyArrow. And however, Polar's team, they built their own Arrow implementation. Like on top of Arrow, they also introduced some new things in Arrow so that things can become more and more uh, efficient in processing data or analyzing data. Um, Arrow also has support for lots of different data types, as we saw. Um, it can also handle missing data very easily. Uh, However, when we use NumPy to handle missing data in Pandas, uh, we face challenges sometimes, and that's what Arrow is trying to overcome. And as we saw, Arrow uses columnar data storage, which means regardless of the data type, all columns can be stored using continuous block of memory, and which makes parallelism tasks easier. So this shows you a performance or benchmark results for three most popular data mining packages: Polars, Pandas, and Vex. And we saw, and we're just seeing right now that for merge, um, Polars took much less time than Pandas. Pandas is green bar, and also for select operations, Pandas took much higher time than Polars. So in both the operation select and merge, Pandas is the Polars is the winner, and Vex is somewhere in between. All right. So now, like we just discussed Rust, like Polars is written in Rust. Now I will show you what are the benefits of using Rust that make Polars faster. So the Rust benefits are its performance, reliability, and productivity. Rust is very fast with no runtime or garbage collection. It can power performance critical services, and it can run on embedded devices and can easily integrate with other languages. Like I just showed you in previous slides, it doesn't have a compiler, so the code can be immediately converted to machine code or machine language for faster processing or execution. Reliability: Rust is a rich type system, and it allows you to have memory safety and thread safety to enable you to eliminate many classes of bugs at compile time. Rust also has great documentation, friendly compiler, and useful error messages, a top-notch tooling, and an integrated package manager and build tool, an auto formatter, an auto completion, and multi-editor support. And that's why more and more new development is being done in Rust these days. So why use Polars over Pandas? Um, because Polar's memory requirement for data operations is much smaller than Pandas. Pandas requires 5 to 10 times as much RAM as the size of a dataset, while Polars require 2 to 4 times as much RAM as the size of the dataset, which is a much big difference. Polars is 10 and 100 times faster than Pandas for operations, and Polars were so this figure on your right side is this shows you um, the results of one of the benchmarks that we used against other solutions. And the benchmark results showed that Polars had performance gains over others due to its parallel execution engine, vectorization, and SIMD protocol. The results of the benchmark showed that Polars can achieve 30 times or 30x performance gain over Pandas. So why it is more efficient for large data sets that we showed you, like for larger than RAM data sets, as the data collection increasing, the data sets are becoming bigger, as I mentioned earlier. And that's where you need Polars. So why Polars allows you to process large data sets efficiently? Because of the rest advantage that we saw, like it compiles code without an interpreter, low resource usage, and memory usage, efficient memory allocation, which enables you to have less copying of data frames, and parallel execution. It utilizes all CPU cores to process multiple instructions simultaneously, and lazy evaluation, which means the operations are computed only when necessary and not uh, all at the same time like pandas pandas does using eager evaluation. So, and that's how polars can process substantial amount of data safely. um, Another reasons, because polars is utilizing apache arrow its underlying data structure. It allows you to work with large data sets using filtering, aggregation, grouping, and manipulation. And Apache Arrow is basically designed for efficient in memory processing and transferring data between different systems and languages. The columnar data that I showed you for Apache Arrow, it enables efficient data processing than rows because Pandas uses a row system. While copy for zero copy While support for zero-copy memory allocation ensures that Polars can handle very large data sets with minimal memory usage. It saves CPU from copied data from one memory to another. What is zero-copy data? It's basically a technique that allows data to be transferred between applications without being copied from one memory location to another. That we do a lot of time in Pandas. And minimizing that can improve the performance of data intensive applications by reducing the amount of time to move data between different parts of the system. What is Polar's query optimization claim? The query optimization claim is basically, as you know, you can use lazy or eager execution, and mostly lazy for Polars. Um, Pandas use eager evaluation or eager execution, carrying out operations in the order of the written code, while lazy strategy evaluates all the operations and maps out the most efficient way to process. So, for example, this piece of code in front of you in the middle, um, it finds the mean of column called number 1 for each of the categories A and B in column category. If this is eagerly executed, the group by operation will be unnecessarily performed for the whole data frame, uh, as Pandas does, and then filtered by category. However, with lazy execution, the data frame can be filtered only for the column called category, and then apply the aggregation of using mean on the column called number 1, rather than reading all the data and then applying group by on one column. So that saves lots of resources and make things faster. How Polars handles larger than RAM data? Again, it uses streaming mode for large than memory datasets on a single machine. Um, Streaming mode uses batches of data rather than all at once, as I mentioned earlier. It's like a for loop processing each batch in turn. However, please note that streaming occurs only in lazy mode, and you need to mention streaming equals to true to use streaming. Alright, Polars can handle some larger than memory data even without streaming. So it's not a hard requirement to use streaming because Polars is designed to handle larger than memory data. However, streaming is one way of making things even faster if you use streaming in Polars. So Polars also have lots of different uh, transformations that it applies on data when you read the data and do slicing and dicing on data. And one of the transformations is called predicate push down, which basically means it applies filter on data frames without reading all data into memory. At the scan level, which means when Polars is reading the file, it applies filters at the same time as I showed you in the previous slides. It applies filters at the source, thereby reducing the amount of data transmitted and processed, so that it can read only the data that you need, and not reading all the data from from CSV file or whatever format of data you have as a source. Polars also offers a Spark-like lazy API for even better performance. The scan CSV command, unlike the read CSV command, lazily loads the file instead of reading the file into memory at once. So this piece of code shows you Polars is using scan CSV and then applying filters as I showed you using predicate push down, um, so that it reads only the column sepal length and only those values of sepal length which are greater than 5, and then using group by on species column to calculate sum for all the columns, and then calling collect function. All right. This graph shows you performance of reading a Parquet file. So Apache Parquet is a format of storing data. It's a column-oriented open source data file format for data storage and retrieval. It offers high performance data compression and encoding, and we use the transformation called to underscore Parquet method in Python to write a data frame to a Parquet file. So the graph, the message of this graph show is that in all the queries that we ran on Parquet format data storage, um, Polars was the winner almost in all the queries, and the color of Polars bar is the purple one. So you can see in Q1, Q2, Q3, Q4, 5, 6, 7, Polars, which is the purple bar, took much less time in processing that query than Pandas or any other um, package like Dask or any other package which I used here. So the idea is that Polars was the winner. It took much less time than most of the other packages, including Pandas. Alright, so this performance benchmark shows you the results of reading in-memory data. So we ran 7-8 different queries, and again, purple bar, which is Polars, took much less time than many other packages for for each of those queries. Pandas took the highest amount of time in all of them, while Polars is is so fast, as you can see. Speed comparison for polars versus pandas. Well, polars is fast for big data for sure, mainly because of the rest advantage that we saw earlier. For example, here we are trying to find sum of 10 million records. We imported libraries, sorry, pandas and numpy, and now in the first case we are using pandas. We are creating a synthetic data set for 10 million rows and 2 columns, and then we are computing sum of each column using pandas. And see, we are timing it to calculate the time it took for that operation. So pandas took 472 millisecond plus minus 6.5 millisecond per loop. While if we do the same thing using polars, the time it took for polars was 14.3 millisecond plus minus 2.2 millisecond. So imagine the difference. It takes 472 millisecond to some 10 million observations. And that's only for 2 features. We just had 2 columns. And the real data often contains hundreds of features, like in big data. So the time will increase exponentially once the sum function is replaced with any complex function, if you are applying any complex transformation operation on the data. So that will increase substantially the time. However, polars just took 14.3 millisecond to some 10 million observations. So in a nutshell, polars is 34 times faster than pandas for the sum function that we just saw. If you want to apply a sigmoid function, for example, to the observations, pandas took 1 minute while polars took 7.8 seconds. So polars is 10 times faster than pandas for apply function. So just imagine how much more time pandas takes to process these types of transformations on data sets than polars, and polars is so fast for such types of operations, especially on big data sets. This following operation was performed on a large data set with 1 million rows. For example, if we imported the data set which has 1 million rows. So pandas took 632 millisecond and polars took 72 millisecond. Such a big difference. And this dataset just had 1 million rows. The real big data sets, they have much more number of rows, like 100 million or 200 million, 300 million rows. That's how the big data sets are big enough. So polars import is 90 times faster in this scenario than pandas import, which is useful when handling large data sets. We can also use lazy load for even faster load and lazy evaluations. So the scan CSV method, as I showed you in previous slides, is a lazy way of reading data sets. And that took polars just 135 microseconds, even less than before. For apply function, pandas took 6.77 seconds while polars took 1.7 seconds. A similar query can be made faster by using the expression system provided by polars. So select is one method that polars uses as part of its expression ecosystem. So if you use select, then it took 382 microsecond, even faster than without using select. For group by, pandas took 7.55 seconds and polars took just 13.3 milliseconds. So polars group by always uses the lazy evaluation system, which means it pushes the query into the query engine and then optimizes it and caches the intermediate results. Finally, the query is eagerly evaluated and then the result is produced. This is much faster than the slow, very slow pandas group by aggregation method. And under the hood, the query statement translate from df.query and dot aggregation to the lazy method of reading it. This is a performance comparison of polars versus pandas for lots of different operations that we use in data science tasks, like read CSV, aggregations, windows functions, inner join and left join. And again, in each of those operations, polars was the winner in terms of the amount of time it takes, which is much less than pandas. Uh, Polars optimization. If you use Polar's lazy API, Polars will definitely run several optimizations. That's how it is designed to work. Some of them are executed upfront, while others are determined just in time as the materialized data comes in. For example, we saw predicate pushdown, which means it applies filters as early as possible at the scan level, meaning when it's reading the data. Projection pushdown, it only selects only the column that are needed at the scan level and not read all the columns unnecessarily as Pandas does. Slice pushdown, it only loads the required slice from the scan level. Common subplan elimination, it caches subtrees, file scans that are used by multiple trees. Polars also simplify expressions using various optimizations like constant folding and replacing expensive operations with faster alternatives, just to make things faster. Join ordering, type coercion, cardinality estimation, several other optimizations that we can use. And besides these, there are lots of other optimizations which are currently being developed by Polars and which are expected to be released in its new versions, which will make things even faster uh, for data science tasks using big data sets. So the syntax and API for Polars, it's very easy to understand. It's quite similar to Pandas. So anybody using Pandas, they can easily switch to Polars and back and forth between Pandas and Polars, as in when required to make their tasks more uh, efficient and faster. So filtering in Pandas and Polars is quite similar. Renaming columns, very easy. Grouping, again, quite similar. The only difference in grouping is that in Polars you just apply group by and aggregation almost at the same in the same line of code, while in Pandas you have to apply to at least two different transformations. Sorting is also very similar. Chaining, column selection, casting, rolling average that we used on usually time series data to calculate several different statistical measures we can use in Polars as well. So again, syntax, on the left side we are using Pandas to read CSV, right side we are using Polars to read CSV. The shape method is similar, dropping columns is similar, writing to CSV files, so similar. Almost same syntax Polars has, so very easy for people to use Polars in their data mining operations. Um, this is for filtering rows, selecting subset of columns, conditional filtering. So on the last side, on the last part of this code, you are seeing conditional filtering. So see, with Polars, you can apply so many things in just one go. Uh, Changing the column name, performing aggregations, applying group by. So quite easy to understand for beginners. All right, so the data support, Polar's data support um, is that it support reading and writing to all common data formats that we see in Pandas too. This allows easy integration of polars into the existing data stack. Um Text files, CSV or JSON, binary files, IPC files, or any type of databases like MySQL, PostgreSQL that we use mostly uh, in data science. Polar support all of them, and especially all the cloud storages that we use for our model building and ML machine learning tasks. Um, like on AWS, we use S3 to store data. So Polar has support for all of them, which is a good news. So what are the data structures of polars? Well, again the same like Pandas, series and data frame. Series is a one-dimensional data structure with all elements having similar data types, while data frame is a two-dimensional data structure and a collection of series. Group by, join, pivot are all operations that can be performed on Polar's data frames. What are Polar's context? So Polar's developed its own domain-specific language, DSL, for data transformation. The two core components of DSL are context and expressions. Context refers to the context in which an expression is evaluated. And there are three main contexts: selection, filtering, and group by aggregation. Uh, so we can use any one of them. So for example, the selection context of polars is applies expressions on columns, um, and a select may produce new columns that are aggregations, combinations of expressions, or literals. So here we are defining one synthetic data set using polars that will have four columns called NRS, names, random, and groups. So if we want to apply a selection context, we can do it like this. So here what we are doing is that we are selecting column NRS and applying sum on it, and then we are applying a sort operation on column names, and also using the first name in column names. uh, we are changing the column name to first name, and to NRS we are calculating the mean of NRS and multiplying by 10 and then renaming it. So much different things can be done in one go in polars, and that's why selection context is very powerful. It allows to evaluate arbitrary expressions independent of and in parallel to each other. Similar to the select statement, the with columns statement also enters into selection context. So the main difference between with columns and select is that with columns, it retains the original columns and add the new ones, while select, the result of select, it drops the original columns and just shows you the new columns. So if you want to see all the columns, use with underscore columns. So the second context of polars is filtering. It it filters a data frame based on one or more expressions that evaluate to Boolean conditions, which is a true or false condition. So here we are saying using column NRS, use only the values which are greater than 2. So the third context of polars is group by. In group by, expressions work on groups and they may yield results of any length, and it can have many members. So here we are applying group by on column called groups, applying aggregate to NRS, and using random to calculate count and renaming it. and then using column random to filter names which are not null, then calculating sum, renaming it, and then changing the order of names in column names, and then renaming the column to reversed names. So imagine now, look, so many things we are applying in just one expression or one context. We were in Pandas, it's not possible to do it all at once. Um, Expressions, we saw context earlier. Now Polars also has concept called expressions, which are the core of many data science operations. So it takes a sample of rows from column, multiplying values in a column, extracting column of years from dates, for example, converting a column of a string to lowercase. So the power of expression is that every expression produces a new expression and that they can be piped together to run simultaneously. All expressions run in parallel separately, and within an expression there may be more expressions. So on the bottom uh, part of the slide you are seeing some Polar's expression example. So see again, it's applying selection on two different things by applying a comma in between. So first it's using column foo, and then it's using column bar for filtering, and all are chained or piped together in one expression using selection. Uh, Two modes of operations, lazy and eager API. In eager, API query is executed immediately, while in a lazy API, query is only executed once it is needed. Well, deferring of execution to last minute can have significant performance advantages. That is why lazy API is preferred in most cases. Here we are reading the file iris, applying filter, and using group by to calculate aggregation. So in this example, we use the eager API to read the iris dataset, which means it reads all the dataset, which we don't want, but here I'm just showing you to give you the understanding. In eager API, it reads the whole dataset, as in step 1, and then it filters the dataset based on sepal length, and then it calculates the mean of sepal width per species. Every step is executed immediately, which can be wasteful, as we may load extra data and use extra resources. In lazy API, we wait on execution until all steps are defined, and the query planner performs these optimization for you using predicate pushdown, which applies filters as early as possible when reading the dataset, so that it reads only rows with sepal length greater than 5. For example, in this example, also uses projection pushdown, so that select only the columns that are needed while reading the dataset, thus removing the need to load additional columns. Here how it is done in lazy API. Scanning the file, applying filtering, group by, and aggregation all at once, and then calling collect. This will significantly lower the load on memory and CPU, thus allow you to fit big datasets in memory and process faster. So when to use lazy versus eager API? In general, the lazy API should be preferred unless you are either interested in intermediate results or are doing exploratory work and you don't know what your query is going to like. In many cases, the eager API is calling the lazy API under the hood sometimes and immediately collecting the result. This has the benefit that within the queries itself, optimizations made by the query planner can still take place. Polar's lazy API is one of the most powerful features of Polars, and we just saw that lazy API allows to specify a sequence of operations without immediately running them. Instead, these operations are saved as a computational graph, and then they are run when they are needed. So this allows pollers to optimize queries before execution and catch schema errors before data is processed and perform memory efficient queries on datasets that don't fit into your memory. So what is Polar's streaming mode? Polar's streaming mode is that it allows lazy API to 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 execute queries in streaming mode. This means that instead of processing data all at once, Polars can execute the query in batches, allowing you to process datasets that are larger than memory. Streaming mode is still in development stages, and not all operations support it. Streaming is supported only in filtering, slicing, group by, and these type of operations. On the right side, bottom right side, you are seeing a piece of code reading this file, filtering some columns, grouping by and aggregate, and then saying streaming equals to true to run in a streaming mode. So here we are just seeing that Polars can handle larger than memory data sets with its streaming mode. Uh, in this mode, Polars processes all data in batches rather than once, and it's useful especially if you're building pipelines that you want to be ready for large data sets in the future. So here we are just comparing Pandas versus Polars. We are creating one data frame with 1 million rows and 100 floating point columns, an integer ID column, then applying a group by on the ID column and take the mean of the remaining columns. So if we compare this query with streaming equals to true and streaming equals to false, it took 75 milliseconds for streaming and 120 milliseconds for non-streaming. For Pandas, this takes about 330 milliseconds for comparison. So, Pandas 2.0 versus Polars. Um, what are the changes? Well, Pandas 2.0 included range of new features towards making Pandas faster and memory efficient to handle complex tasks. Um, it included the most robust memory management called PyArrow. So, and it also allows users to choose between traditional NumPy backend or the brand new PyArrow backend. Mm, PyArrow is a Python interface for handling large data sets, basically using arrow memory structures. Another feature that it introduced is called copy on write, which is a very big breakthrough, and that allows to improve performance by saving lots of memory resources. So what it is? So it keeps a lazy copy of Pandas objects, such as series and data frames, rather than cached copies of objects. These methods return views when copy on write is enabled, which provides significant performance improvement compared to regular execution in Pandas. So what does it mean is that in Pandas, whenever you need the data, it calls the original copy so that it, it copies the data multiple times. However, if you enable copy on write in Polars, it just keeps one copy of the data and that reuses that again multiple times as and when needed, rather than copying the data lots of times as and when required. This saves lots of memory resources. This is a performance comparison chart of Pandas and Polars for tests like import, group by, rolling statistics, sampling, compound manipulations. We can see Polars as the winner in each one of those tests, mainly because of the features that we saw, like the rust advantage, the memory usage, the parallel processing, multi-threading, and the lazy execution of code. What is new in Pandas 2.2? It's released on January 19th, improved by arrow support, like list and structures were NumPy object data type before. Now arrow provides much easier way for lists and structure. This is a series that contains a dictionary in every row. Previously, this was only possible with NumPy object data type, and accessing elements from these rows require iterating over them. So as you can see on the bottom right, defining a series, and then we are using arrow method to call it. So the struct accessor now enables direct access to certain attributes, which was not possible earlier. We are calling pa.struct for keys, project, and version. And if we call one of the keys called project, it shows you the values inside that. That's how easy now it is with arrow. Integrating the Apache ADBC driver. Well, Pandas mainly uses SQL Alchemy to read data from SQL database. So Pandas allows you to make a connection via Python to databases or data lake, wherever your data is stored. And it uses SQL Alchemy for those operations. And Alchemy reads data row-wise, while Pandas has columnar layout, which makes reading and moving data into a data frame slower than necessary. However, the ADBC driver from Apache Arrow project enables users to read data in a columnar layout, which provides huge performance improvements. And the ADBC driver, it supports both PostgreSQL and SQLite. It also introduced case managed statements like we have in SQL or PostgreSQL, so that you can apply if-else conditions much easier now in Pandas. Polars for ETL. Well, ETL, called extract, transform, and load, is a process of combining data from multiple sources into a large central repository. Imagine you have data residing at several different locations and you want to integrate that data and then load that data into your in-house database for analysis. So Polars support that as well. Polars provide speed, simplicity, fast in data ingestion, and no memory constraint, which are prerequisites for a successful ETL operation. So Polars definitely support ETL tasks to extract data, to transform the data, to clean the data into whatever way you want as per your data lake or database requirements or your schema requirements. And then it allows you to load that data in your data warehouse. So when should we stick with Pandas? Well, Pandas is a good package for small to medium scale projects, and is still the best package in many scenarios like data exploration and machine learning because of interoperability and tooling. Like Polars has extensive interoperability with packages using Arrow, but not compatible with Python data visualization and machine learning libraries like scikit-learn and PyTorch. However, Plotly does support Polars. So still lots of things Polars can't do, so Pandas is the way. But with moving forward, Polars will introduce new and better way of doing things, and it will allow much more interoperability with the other features like data visualization and machine learning libraries like scikit-learn and PyTorch. Polars provides to be faster for data manipulation. However, Pandas is still the best for data exploration and machine learning tasks. As the Python ecosystem evolves, the compatibility gap between Polars and other libraries may narrow, making Polars an even more compelling option in the future. How can we improve data mining performance? Well, we can improve data mining performance by reducing copying with copying on write, as I explained you in the previous slide. In traditional data manipulation tools, every data operation leads to a creation of a new copy of entire data frame. And this behavior can be problematic for memory resources while dealing with large data sets. So copy on write is the way to go. It's a technique to solve this issue. It's a resource management technique that enables uh, efficient implementation of a duplicate or a copy operation. And that means that if a data set is duplicated but not entirely modified, it is not necessary to create a new resource. Instead, the memory resources can be shared between copy and original. Parallel computation is another way to improve data mining performance. Like Pandas is threaded, not multi-threaded, and it does not have parallel computing. So parallel computing is done by either multi-core machines or distributed computing, like a group of computers working together in a cluster. For example, in this data set on the bottom right, we want to calculate mean age of all basketball players grouped by teams. We could use parallel computing here. It's a good example of parallel computing to apply. So we can assign calculation of mean of each group to one core or machine instead of calculating one by one like we do in Pandas, so that we can improve the performance and make things faster and utilize the memory or computing resources like the cores in your CPU more efficiently. Another ways of improving data mining performance is optimizing data import. Like reading large data set is oftentimes consuming in Pandas, so Polars provides faster alternative. Some techniques that can improve performance when reading data files are data chunking. So instead of reading full file, we can break it into pieces like chunks. This allows faster data importing while reducing memory required to store it all simultaneously. It can also read only the required columns instead of reading the whole data set, applying filtering uh, context that we saw earlier, and downcasting data types. So tools like Pandas, they have a behavior that when assigning data types to imported columns, uh, it has to assign all of the respective data types. Like it cannot store data, a Pandas data frame, without assigning the uh, data types, while Polars allow you to do that using downcasting without losing any information. Lazy evaluation and query planning, as we saw earlier, the order of operations definitely affect performance. So we can reorder some computations and get same answer more efficiently. And the methods are lazy evaluation and query planning. Lazy evaluation, as I showed you earlier, is a process of delaying computations until they are needed, while query planning is a process of finding most efficient way of performing multiple data manipulations given a set of queries. And out of core processing is also another way. Like Pandas store entire data sets in memory, which is not efficient when working with large data sets. So out of core processing means you can use external memory to store your data for data that cannot fit in your available memory, and it gives the same results. Some high performance Pandas alternatives are Collas, Vex, Modine, QDF, um, which are besides Polars trying to provide the same uh, performance to improve shortcomings or performance bottleneck of Pandas. But Polars is definitely stronger in each one of them, especially for large data sets. So why choose polars? Because Pandas is most widely used. It has limitations when dealing with large data sets. And the core mission of polars is to offer a lightning fast data frame library that addresses the problems of Pandas. It's written in Rust, um, and it integrates state of the art methodologies to increase performance, allows you to have parallel computing, provide storage performance improvement using copy and write and Apache Row. And the important feature of Polo is that it has a very similar syntax to Pandas and share the similar data structure under the hood. Um, this is the way Polars executes the code. Um, in the top cell, you can see that we are reading a Reddit CSV file using Polars, and it takes each line of code, it adds to an internal query graph that it creates internally, and then it optimizes the query graph. So when we execute the code in Polars, it executes the optimized query graph by default. Execution on the full data set. This is we are using full data set. So we saw that from 10 million rows in this data file called write.csv, there are just 14,000 rows that match our requirement in the bottom piece of code. So otherwise we would have read 10 million rows, but now we just need the data from 14,000 rows. So it's definitely improvement in performance. And we can use collect method to process data as one batch. Execution on large and in-memory data. If data requires more memory than available, Polars processes data in batches using streaming. Using streaming equals to true. Execution on the partial dataset. So while writing, optimizing, or checking query on large dataset, querying all available data may lead to a slow process. So we can use a fetch method that fetches only the rows that you need. Here we say just fetch 100 rows for that data, for that amount of data that we need as per this query. Query optimizations. If you use Polars API, it will run several optimizations on the query. So how Polars will make your life easier? These are some of the features that make life easier using Polars. It's easy to use. It's embarrassingly parallel. Lots of parallel processing does go on under the hood. It uses Apache Arrow, which is a very, very efficient memory storage format. It's close to the metal, meaning it uses Rust and converts code into machine code right away. And it uses out-of-core processing. It eliminates the need to keep all data in memory, thereby using memory more efficiently. Multi-threading and parallel computing. Multi-threading is basically it's a concurrent execution of more than one sequential set of instruction, and it's programming multiple concurrent execution threads simultaneously, and these threads run a single processor, or there could be multiple threads running on multiple processor cores. Well, multiprocessing implements parallelism, and it allocates separate memory resources for each program or process. But multi-threading shares the same memory resources for threads belonging to the same process. So basically, overall, what it means is that in multiprocessing, we can assign subtasks from the main task to different parts of your CPU and memory. While multi-threading uses the same memory, and divides a task so that all task is assigned to the same part of the memory, which is not very efficient. So in general, multiprocessing is more efficient. So here it's how it is done. Um, Multiprocessing adds CPUs to increase computing power, while multithreading creates multiple threads of a single process to increase computing power. The bottom right is the chart showing that. So polars in big data analysis, machine learning, and data science. Well, in data analysis, uh, processing large data sets is very crucial. So polars definitely provides benefits there. In machine learning, again, it involves working with large data sets and requires efficient data manipulation. So polars capabilities can speed up these processes. And for data science overall, which involve extracting insights from data, often requires efficient data manipulation. And polars, with its wide range of features for data manipulation, can definitely help data science tasks to run more efficiently. All right. So conclusion is that um, and then after this, I will show you the demo in the Jupyter notebook. But let's see the conclusion. So using pandas and polars together, we can make data processing tasks more efficient, swap out the parts that are slow with polars, and leave the rest of the code in pandas. It's easy to switch between pandas and polars. We can convert a pandas data frame to polars. It's very easy as well, and vice versa. And this facilitates refactoring existing code to use third-party libraries that only supports pandas. In general, Polars is a very powerful library for handling datasets, large datasets especially, complex data types, and it offers easy integration with other Python libraries such as NumPy and PyArrow. Polar's optimized backend, easy syntax, lazy API integration with Python ecosystem, it makes the library stand out among the crowd. And the core mission of Polar is to provide seamless data processing experience on any scale. So, to sum up, when working with big data sets, performance improvement is crucial. So, Polar takes the charge to improve the performance. Now, I will just quickly show you a demo in Jupyter Notebook to show you how it's done in real uh, scenario. First, we installed Polars, then we installed Pandas, then we imported all the libraries. Here I am creating a data frame, then I'm reading the data frame using lazy execution, then I'm manipulating a data frame using selection context. Here I'm merging two data frame using polars. It's very similar to how we do it in pandas. Here I am handling missing values in polars. Here I'm applying functions on the polars data frame. Um, this is another example. I'm reading a diamond data set from this link using polars, and I'm applying selection and filtering context on that data set. I'm just selecting 3 columns here, and now I'm filtering rows based on certain condition using filter method in polars. Here I'm sorting and ordering the data using polars. Here I'm handling missing values using polars. It provides convenient methods to handle missing values. Here I am grouping the data based on specific columns using polars. Now I'm joining and combining the data frame using polars. The synthetic data polars versus pandas comparison. Here I am creating a data frame which will have 10 million rows and 4 columns, just to show you how the performance is different when we apply several function transformations using pandas and polars. So here I'm reading that dataset of 10 million rows using Pandas, and it took 1.6 seconds for Pandas to read, while Polars took 0.56 seconds. So Polars was 64, almost 65% faster than Pandas. Here I'm filtering rows on that data based on condition, so that reads only that data. It took 132 milliseconds, while Pandas took 1.29 seconds. Here I am creating one synthetic sales information data set and then reading it. So this data set I'm creating, it will have 22 million rows. These are the functions I use for reading comparison and plot comparison. So here I am reading the data set of 22 million rows using Pandas. It took 19 uh, um, milliseconds, and using Polars it took just 2.3 milliseconds. See, the Polars is the green bar, much smaller than others. Pandas with numpy or Pandas with pi arrow. Here I am applying group by an aggregation test, but before I do that I had to convert the date column to date time format using this part of code. Then I applied the mean aggregation. So to apply the mean aggregation, you use group by on office and date, using those features on the sales column, and calculate mean of them, of sales column. It took Pandas 1.7 seconds and Polars just 0.13 seconds. And for median as well, it took Pandas much higher time than Polars. For rolling mean calculation, took Pandas again much higher time. Well, to find sum of 10 million observation, let's say I create a data frame here which has 10 million rows and two columns called A and B. To sum the columns using Polars, using Pandas it took 161 millisecond and Polars just 2.86 milliseconds. Such a big difference. So this was just to show you the difference in performance for both Pandas and Polars. So alright, so this sums up the course. I hope you enjoyed this course, and please provide your comments, suggestions in the comment section of the video. And if you want to be informed about my future videos, do subscribe to this channel so that you get to see all my next videos on data science um, um, topic. So thank you very much, and God bless you.